Okay, so uh, let's see. Somebody asked if I could put the PowerPoint in kind of a larger style format. You know, the PDFs right now on the website are like 4 per page, and I just when I looked at them, I realized that's kind of annoying. And you guys all have tablets and computers. There's no reason to have that them that way. It's kind of back when everybody printed everything. So on the iLearn, we mostly have one last lecture, and then we might actually jump into alkynes today. On the iLearn, I posted the last lecture, the 7th lecture, in full format, and the others will be maybe up by tomorrow on the public website. But if you want that one, it's a pretty intense one. It's gonna be fun because we're actually going to be solving problems. You can go just check on the announcements or whatever of the iLearn format thing. All right. Okay, so we're cool. Let's see what else. 1 second. Okay, so yeah, where were we? We're finishing the 6th lecture, which is the carbon 13 NMR, right? And I showed this as a cool example of, you know, the beauty of carbon NMR. This is a, you know, it's not a totally crazy molecule, but we got some different carbons and stuff. We see every carbon. Each carbon is represented nicely. Remember the double-sized peaks tells you there's probably more than one carbon, right? We don't use integration. We don't really use splitting, but we do see like largeness of peaks and kind of like where the peaks are, right? And then the ketone is 211, way down on the left, okay? And I also kind of ended by saying I ended by saying, you know, the proton of this is actually kind of complicated because rings are often complicated. And I showed the proton and I was like, that's pretty complicated, right? So this just shows that like sometimes a carbon just tells you so much more maybe than a proton. Proton is great in a lot of situations, but sometimes like this molecule, there's not too much exciting stuff to see in the proton, right? Okay, so we already talked about this. Yeah, which is easier to interpret? Probably the carbon, I'd say, right? Okay, but in the end, they're both tools you have. And if you become a research chemist, you use this stuff every day. You do protons and carbons left and right. My undergrad research students right now, we were just talking about a proton NMR just a second ago. And, you know, research, if you do research, you're doing proton and carbon NMR like a couple times a day, right? It's fun. Okay, so yeah, where does the proton NMR show the ketone? It doesn't really, because the ketone does not contain a proton, right? Right? Okay, so now we're going to do something fun as a little ending bit on carbon. Dept 90 and Dept 135. I think I'm pretty sure the book mentions these. These are pretty cool techniques. They have a great acronym. If you love acronyms, you'll love this. They're distortionless enhancement by polarization transfer. And if you want to impress your friends tonight, say, guess what? I learned about distortion and enhancement of polarization transfer. And then they're going to think you're crazy. Okay, so what are they? It's just a variation of carbon NMR. It's a variation of carbon NMR, right? And it's a cool variation of carbon NMR. Normal carbon just shows a bunch of peaks, and they're all upward, right? And they're all singlets, right? That's what a normal carbon is. Dept 90 will only show CHs. It's this really crazy technique that it filters everything out but CHs, and CHs go up. Kind of cool, right? Because you can figure out which of your things are CHs. Dept 135 is a tweak on that, and it shows CHs and CH3s upward and CH2s downward. So it pokes the CH2s downward. It's a weird NMR magic thing. And you know, the theory of it, I don't really understand, but this is also something we can do on the machine at SF State. You tell it, I want to do Dept 90, and it just does it, right? Okay. And then Dept eliminates quaternaries. So any quaternaries are gone. That's the only thing. Do you need to memorize this? You don't need to. You're probably never going to see it again, just because but unless you take, you know, an advanced NMR class, or you know, if you do research, you might see these. So, but don't worry about, oh, do I have to remember Dept 90 does this and Dept 135 does this? You don't have to memorize that. But let's see the magic of this. First we're going to do a silly molecule, then we're going to do a crazy molecule. Okay, so this is ethylbenzene, simple molecule. You got a benzene and an ethyl group, right? There's your benzene. There's, if you count the peaks, it's probably 1, 2, 3, 4 peaks in that aromatic region, right? There's four distinct carbons. The quaternary, this pair of CHs, this pair of CHs, and the little CH, right? You can see that little peak there. That's probably, which one's that? That's probably going to be this one right here, okay? Okay, then we have the ethyl. We have 2 carbons, CH2, CH3, right? Nothing too crazy, right? So what happens, make a prediction, what's going to happen when I do dep 90, which is only CHs? Well, these are going to go away because they're not CHs. It's a CH2 and a CH3, right? So dep 90, look at that. There we go. The CHs are there, right? And what about dep 135? Now the CH2 goes down and the CH3 goes up. So that's a really cool trick, especially if you stack them. You can see all your carbons and figure out, well, that's a CH2, that's a CH3. These are all CHs. Again, a silly example. Let's do a crazy example now, all right? So strychnine. Strychnine is a complicated natural product. It's a poison. It's actually still used, I think, as a rat poison. So it's a complicated alkaloid, nitrogens and chirality, lots of fun stuff. Let's just guess how many CHs there are. You don't have to guess, you can count them, right? How many CHs are there? I could have you vote on it, but I'll do it, I'll help you. On the benzene, we got 4, right? 1, 2, 3, 4, right? There's 4. Any CHs over here? Not really, no CHs. These are CH2. Okay, so we have 4, this is 1, that's 5, 6. The alkene has 1, that's 7. And there's also 1 right there, that's 8. We're not showing it, but it's there, that's 8. Any more? I think there's 1 right there, that's 9. So there should be 9 CHs, right? All right, so here's the normal carbon. It actually, if you look at the proton of this is a very crazy molecule. The proton's pretty difficult to interpret, but this shows all the carbons. That's kind of cool. But now let's see if we counted 9. Let's see if there's 9 CHs in the dep 90. Look at that. So a lot of the peaks disappeared, and now we got 1, 2, 3, 4, 5, 6, 7, 8, 9. Beautiful. So now we know which of the carbons are CHs, right? Kind of cool. How many CH2s are there? There's 1. There's 1. That's 2, right? I think there's 3 and 4 and 5 and 6, I think, right? 1, 2, 3, 4. Let's try it again. 1, 2, 3, 4, 5. I see 6. I think that's right. So those are all going to be, and I do the 135, those are all going to poke down, okay? 1, 2, 3, 4, 5, 6. And the CHs go up, right? Any CH3s? I don't see any CH3s. There's no methyl groups, right? So the things that are up in the 90 are the same things that are up in the 135, right? And remember, the other thing about dep is that the carbonyls, the quaternary, which I think are like these guys, we have 4 of them. 1, 2, 3, 4. Those go away in the deps. So the carbonyls, like the amide, there's 1. There's this one, this one, this one, and this one. I think that's all. Maybe there's 5 of them. There's 5, I think, but another one's buried somewhere. Okay. Anyway, that's dep. It's cool. It's a neat kind of research technique that you use in NMR. Certainly for complicated molecules, it really helps you. Oh yeah, questions. Which are the CHs and CH2s? Well, we figured that out, right? There's the CHs, there's the CH2s. Where are the CH3s? Well, there's no CH3s. And which are the quaternaries? We have at least 4. There must be another one hiding somewhere. It's maybe buried somewhere, but yeah. All right, dep. Distortionless enhancement of polarization transfer. What did carbon tell us? Overview. Each different type of carbon has a peak. The chemical shift gives a clue as to the type of carbon. This is an alkane, alkene, benzene, carbonyl. Integrals are not used, but sometimes the size of the peak tells you something, like big peak, multiple carbons, right? Spin-spin splitting is suppressed. We turn it off with that weird decoupling technique. And then these depth, and then actually that's funny because remember that the spin-spin splitting told us, oh, CH2, CH3, remember that? We're like, it's a triplet, it's a quartet, but those are huge triplets, huge quartets. So this is kind of useless. Nobody does spin-spin coupled carbon NMR. Nobody in the world. We only teach it, but we don't do it. Rather than use the splitting to figure out CH2, CH3, right? We would use depth, okay? Okay, so we introduced this. You're probably not gonna see it again in the course. Maybe in a homework problem, you might see depth again, but now you know the basic idea. It's not that crazy. Okay. All right, now the grand finale lecture. You know, it'd be cool if we could just jump to this, but you can't do this until you know all that other stuff, right? So that's why we get to this point. But this is going to be the kind of problems that we'll see like in the homework, for example. How can we use NMR to determine a chemical structure? That is a crazy question, right? By that, I mean, I give you an NMR and you figure out the structure. Sounds horribly terrifying, right? Like, here's an NMR, what's the structure? And if you don't do it the right way, it is horribly terrifying. But there's a systematic process that we can use that works almost every time. And I have to teach you that process. I don't think the book actually describes a systematic process. So this is kind of what I came up with. I actually came up with this in grad school in Santa Cruz, kind of as a way to teach this. It's fun. It turns it into a puzzle. Okay, so all you got to do is figure out the pieces of the puzzle, and then you got the structure. That's pretty much it, right? Okay, first thing. Now this. Oh, somebody's from Santa Cruz. Yeah, woohoo, slugs. Okay, so first thing we need is you to be 100% competent on degrees of unsaturation. This is something I brought up in my Organic 1 lecture kind of at the end. We didn't really go through it that much, but you need to have this down. And if you can't do degrees of unsaturation, you're going to be completely lost. So this is the strategy. It's UN is equal to 2 times the carbons minus the hydrogens plus 2. Divide everything by 2, okay? If you have oxygens, you ignore them. If you have halogens, you add an H before the formula. Before the formula, you add an H, your molecular formula. You have a nitrogen, you subtract an H. So we'll see this, we'll practice it, but you gotta, if you're having trouble with this, you need to ask at office hours or something, right? Okay, so that's the first thing. That's the first thing, is we calculate degrees of unsaturation. The next thing is we create a table. So we're going to look at the NMR, and we're going to create a table that contains the relevant information from the spectrum, from the NMR spectrum. And we're mostly going to focus on proton right now. Carbon sometimes helps, but we can do everything with proton. Chemical shift, which is the position on the x-axis. Splitting, which is the like singlet, doublet, triplet, right? And integration, which is the number of H's in the signal, right? Create this into a table. Convert each row of the table to a substructure, which will account for all the atoms in the molecular formula. So that would be, what do I mean by substructure? A CH3. How many attachments are there on a CH3? There's 1. And I say squiggly line. We have 1 squiggly line on a CH3, because there can't be 2, because that would be 5 bonds to carbon, right? So we use the valency of carbon to figure out the substructure and the squiggly lines, right? Like a CH2 will always have 2 squiggly lines, right? How many squigglies would a CH have? You have a CH, how many attachments are there on the CH? Maybe 4 minus 1 is, anybody know math? 4 minus 1, nobody has it. All right, I'm gonna teach you elementary arithmetic. Okay, so yeah, a CH would have 3 squigglies, right? So you draw the squigglies, right? And then sometimes it'll be like a ketone. We'll figure out how we determine there's a ketone. Sometimes it'll be a benzene, and I'm showing a disubstituted benzene. It could be a monosubstituted benzene, or it could be a disubstituted benzene, right? There's all these kind of things. Once you got the pieces, we attach the substructures to make one or more candidate structures. And those would satisfy the rules, like your splitting rules and stuff. Often you'll just jump right to the answer, and then you're done. The whole point is to figure out the answer, right? But sometimes you'll come up with two, and you're like, which one's more consistent, right? Pick the candidate that's the most useful, most consistent, okay? All right, so one more thing. Remember, usually when I do integration, I'm gonna just give it to you. Remember that everybody hates the red lines? I'm gonna try to avoid that and just say, all right, it's 2 to 2 to 3. That makes it easy, right? Still, it can be complicated because 2 to 2 to 3 is relative, right? 2 to 2 to 3 could also be 4 to 4 to 6, right? 2 to 2 to 3 is proportional to 4 to 4 to 6. So how would you know, is it 2 to 2 to 3 versus 4 to 4 to 6? The answer is the molecular formula, right? Because if I tell you there's 7 hydrogens, if I say, hey, there's 7 hydrogens, well, then you know it's 2 to 2 to 3. What if I tell you there's 14 hydrogens? Well, if it's 14, it's probably gonna be 4 to 7, right? Okay, so the molecular formula will resolve any confusion. So therefore, the above example could be 2, 2, 3, 4, 4, 6. And to know for sure, look at the molecular formula, okay? All right, problem 1. So we're gonna just use my formula, my technique, and we're just gonna solve this. I'm gonna switch to my second webcam to do this on paper. You should try to follow along on paper, right, as I do this. All right, so I'm gonna get to Zoom and say, let's see. Oh, I see. You see my trash can. Whoops. Okay, so I basically printed out all the slides from now on, and they're on paper, so I can actually write on them. Okay, this is problem 1, and we're just going to go down the list and the strategy, right? I see somebody already said UN equals 1, and you are right, but let's just do the math. UN is definitely 1. So the way we do it is we ignore the oxygen, right? So this basically becomes C5H10. And then I do, remember it's 2 times 5 minus 10 plus 2 over 2. What's 10 minus 10 is 0. 2 over 2 is 1. Okay, very important. This is the key to this problem, this little bit of information, okay? So we did that, we determined UN. Now we tabulate the NMR data. So I'm gonna make a little table. I'm gonna say, the abbreviation for chemical shift is delta. Splitting H, that's my table. Okay, delta is the chemical shift, splitting is the splitting, H is the number of hydrogens, or the integration, right? So delta, I can go left to right, I can go right to left, doesn't matter. I see 2.6. The splitting is maybe a hextet, I don't know, pentet. It's a bunch of peaks. And the cool thing is, it doesn't really matter that I figure out exactly what this is. I'm gonna say mult for multiplet. Okay, you'll see why it doesn't matter in a second. Mult, it's just all that means is whatever's around it, there's a bunch of things around it, right? H, what's the H? Well, and you know, there's 1 to 3 to 6, so it adds up to 10, that's good, right? So, but the H is 1, right? 1. Okay, and then now this looks like a nice singlet at 2.2. S for singlet. H is 3. You cool? We're all cool. I think we're all cool. 1.1 looks like a doublet of 6. And remember, usually things that are around 1 are multiples of 3, right? Okay, so we tabulated, now we identify the substructures. To do this, generally speaking, I just look at the integration. That usually helps. Like 6, what's 6? It's maybe 2 somethings, right? 2, what are,
2 CH3s.
2 CH3s, absolutely. So I'm going to draw 2 CH3s. Squiggly line and squiggly line, right? We have 2 CH3s. That is what 6 is, right? What about the top? Well, actually, what there's 3 here is probably 1 CH3, right? Now, it's a possibility it's like 3 CHs. You'll see that that is, you'd run out of carbons, and so that's impossible. Most likely, if you see 3s and 6s, most likely it's just CH3s, okay? So yeah, it's another CH3, a different CH3. Okay, we have CH3, we have 2 CH3s. What about this? 1 we said was, let me say it. It's obviously 1 hydrogen, maybe a CH. And how many squigglies did we determine are on a CH?
3.
3. So it's a CH with 3 squigglies. Cool. All right. We're almost there. It looks still daunting, right? How are we going to turn this into a chemical structure? Well, there's another kind of mini step, which is kind of like 2.5, I guess, is I'm going to say, are there any mystery substructures? Mystery substructures. Are there any mystery substructures? By that, I mean a substructure that's not represented in the table. And to give you a hint, are there? Well, I don't know. We have 4 carbons and there's 5 carbons though, right? We accounted for the hydrogens, right? We counted for all 10 hydrogens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We got all the hydrogens. We're missing a carbon. What about that oxygen? Is that oxygen here somewhere? No, it's not. What about UN equals 1? Did we account for that? And what does UN equals 1 mean again? It means either a ring or a double bond, right? The definition of this UN thing is rings and double bonds. Generally speaking, it's going to be double bonds for you guys, all right? So how could I account for an extra carbon, an extra oxygen, and that UN equals 1? Maybe a mystery substructure, or another way to say that is maybe a mystery functional group. Like a mystery functional group that contains a carbon and an oxygen and a double bond. Any guesses?
Ketone?
That's exactly it. Totally ketone. Okay, now why not aldehyde? Because the aldehyde is also a carbon double bond oxygen. Why not an aldehyde? Well, that would come at 9, right? Right? Remember, aldehydes come way at 9. We don't see that. So there's no way it could be an aldehyde. It has to be a ketone. There's one option and one option only, it's a ketone. So we draw that. Okay, that's a mystery functional group. It has to be there. There's no other option. No other option. You can go through your entire list of functional groups that you know. There's nothing else that's a C double bond O, right? An aldehyde is, but that has a peak at 9, right? Carboxylic acid, yeah, carboxylic acid, but that has 2 oxygens. What about an ester? An ester has 2 oxygens, so can't be an ester, right? We'll see esters in a bit, but yeah. So now we've finally finished step 3, right? I guess, yeah, this is kind of part of step 3, I guess. Yeah, maybe it's it's almost like part of step 3. You got to figure out any mystery substructures. If you don't have them, if you can't figure it out, you're stuck. You're never going to solve the answer if you can't figure out the mystery substructures, right? Okay, now we generate candidates, which means we start snapping things together, right? Now, the way I do this systematically is I look around here and I look for ways, any information that might connect these. And I see that D, and the D stands out like crazy. Because what does a D mean? A D, those CH3s, how many neighbors do those CH3s have? It's a D means, remember N+1 rule. Like D is 2, but if you're going the other way, it's like you subtract, like double this, you know, it means, basically means there's one neighbor, right? 1 + 1 is 2, double it, right? The D means these CH3s are connected to something, right? What are they connected to?
The CH.
The CH. It's the only possibility, right? The D just solved the problem for us because now we know these guys are connected to that guy, right? So I can kind of now, sometimes it's good to have an eraser at this point, but I'm going to make an assumption that now we have a CH, CH3, CH3, right? Whoops, CH3. See that? It's an isopropyl group, right? CH3, CH, CH3. We determined that these guys are connected to that one, right? These two are connected to that one. So now I'd probably get my eraser out if you got an eraser. We just infinitely simplified the problem. You have a ketone with a methyl on one side, isopropyl on the other. And we solved it, right? Ketone, I like to say, in this situation, I have 3 substructures, right? 2 are end pieces. I got an end piece and end piece and a middle piece, right? Whenever you got 2 end pieces and a middle piece, it's not rocket science to put them together, right? This is on one side, this is on the other. So the answer is this, right? It's isopropyl methyl ketone, or you could draw it if you like. Those are the same, right? It's a pretty cool process. And now we have like a bunch more examples. It gets a little easier each time too, because now we get the process. But that's going to be the goal, is given the data, figure out the structures, right? And this is a pretty systematic universal method. UN, tabulate, identify substructures. And if you have a mystery substructure, you can't continue until you have it. If you have not accounted for all your carbons and oxygens and everything, you can't continue. It's impossible. So don't even attempt to go to step 4 until step 3 is done, okay? And we pick the best candidate, right? Fun. Let's do the next one. Any questions on this? It's a pretty easy one, and they get a little harder, but this is a good start. All right, number 2. All right, so UN. First start with UN. Remember that oxygen you ignore. So all I do is I just say, well, it becomes C10H10, H12, sorry. C10H12, right? Do the math. It's 22, you know, I just say 2 times that plus 2 becomes 22 minus 12 all over 2. 22 minus 12 all over 2. I think that would be 10 over 2 equals 5. Well, that's a big number. That's scary, right? 5. How are we going to account for 5? Well, first thing, and you know, first thing about larger numbers of UN, what's a benzene? Let's just draw a benzene here. What if we have a benzene? What is the UN of a benzene? Well, because remember, a benzene is a ring and 3 double bonds, right? A ring and 3 double bonds. So this is going to be 4. This is always, benzene is always 4. It can't be 3, for example, right? If I have 4, it's a benzene. So when I say 5, I'm like, maybe it's a benzene plus something else, right? It's a benzene plus 1. It's 4 plus 1, right? So UN equals 5. UN equals 5 probably means benzene plus 1. Now I also immediately, looking around here, I'm like, whoa, what comes at 7? What comes at 7? You can go look at your chart on the syllabus or whatever. Only one thing comes around 7 or 8, and that is a benzene. So yeah, benzene, right? Okay, so that makes it easy. Let's keep going though. We started with UN equals 1. We tabulate the NMR data. So now I'm going to do delta splitting H. Delta splitting H, okay? Delta. This time I'm going to start on the right arbitrarily. 1.2. Looks like a doublet of 6H, right? 3.5. Remember, all these are on the iLearn as huge PDFs, so you can print them or whatever you want to do. 3.5, right? Septet. I tell you septet here. But if you can't count all the peaks, you might just say multiplet. Because remember on the last one, we didn't even figure out. Oh, we said, oh, it's a multiplet, and then we got the answer. Septet, multiplet, it doesn't really matter. All we know is there's a bunch of stuff around here, right? Okay, and that's 1H. Okay. Now what are we gonna do with this thing? Well, it looks like it's a mess. So we could write mess here or multiplet, I don't know, whatever, mult. And it ranges from about 7 to 8, whatever, 7 to 8, all right? And then, but what's the number of H's? It's 5. Okay. Now, of course, this 5 is totally independent of this 5. Those are not connected concepts at all. Let's make the substructures. We'll do the easy ones and then the slightly more confusing one. So 6H, we did that last problem with 6H, around 1 ppm. Same thing as before. 6H, 3H, 2 methyls. Okay. Single CH, probably a single H is probably a CH, right? So it's a CH with 3 squigglies. CH with 3 squigglies, right? Now this crazy thing, how are we going to interpret this? Well, we said it's a benzene, right? It's a benzene. Now, okay, so this benzene, it's a benzene, right? This benzene, how many squigglies are on the benzene? How many squigglies are on the benzene, meaning attachment points? And this is really important because that's, if you don't do that right, it's not, the problem's not going to work out. But how many attachment points? Let me give you a hint. There's 6 carbons, right? And there's 5 H's. So it is a single squiggly, right? 5 H's means mono-substituted. It's a mono-substituted benzene. So yeah, it's a single squiggly, okay? What if it was 4? If you had four CHs in the aromatic region, then it would be a di-substituted. And then you'd have to do 2 squigglies, with the only issue being, is it ortho, meta, or para, right? It could be ortho, it could be meta, or it could be para, right? Remember that whole thing? Ortho, meta, para? But, and we also, if you go back a few lectures, when we talked about that, remember there's a trick to ortho, meta, and para. Like, I'm not going to do all that right now, but remember, ortho was like 2 doublets, 2 triplets. Meta was 2 doublets, a singlet, and a triplet. And para was 2 doublets. Remember, we did this. We did a whole slide, a couple slides on this. But this is easy. 5 means this. What's a word for this? It's mono-substituted. Mono-substituted, right? as opposed to if it had a couple of squigglies, it would be disubstituted. Okay, all right, so we got some pieces. Are we done with step 3 yet? Yes or no? Identify substructures. Part of what we have to do is check the molecular formula now. And it looks like I have, how many carbons? 1, 2, 3 plus 6 is 9. Uh-oh, extra carbon, right? H's, I got 3, 6, 7 plus 5 is 12. Oh, good, we have all the H's, good. Uh-oh, we're missing an oxygen. So we got the same situation as last problem. We have a carbon, we're missing a carbon, we're missing an oxygen, and we're missing a UN, right? Because the UN is 5. We've accounted for 4 UN, but not the 5th UN, right? So we say it's a carbon, oxygen, and 1 extra UN. Just like the last problem, the mystery functional group begins with a K, ketone. It's another ketone. Okay. All right. Okay, I'm just going to draw that somewhere. All right, so now the attachment of this is really easy. The attachment of this is really easy. It's the same strategy. The D tells you everything, right? What does it tell you about the 2 CH3s? They're connected to the CH. You got an isopropyl. It's drawn really terribly. But the answer is, now it's the same thing. We have 2 end pieces and a middle piece, right? 2 end pieces. End piece means 1 squiggly, right? We got 2 end pieces, we got a middle piece. Only one way to connect them. There's only one way you can answer this. It's benzene, ketone, isopropyl, right? Benzene, ketone, isopropyl. So now, that's the answer. You can draw it any way you want, but it's a benzene, ketone, isopropyl. Okay? 2 end pieces and middle piece. All right? Next. Any other questions on this one? And it gets a little easier each time. And remember, somebody said, can we say functional groups are always going to be the middle pieces? Somebody said, their question was, can we say that functional groups will always be the middle pieces? Well, no, you can't say that, because a middle piece is something with 2 squigglies, right? So sometimes the middle piece will be an ethyl, like a CH2, right? Like a CH2 has 2 squigglies, that's a middle piece. So you cannot always assume that the middle piece will be like a functional group. You cannot make that assumption. Every problem is different. All right, cool. Next. All right. So now I got rid of the instructions, so we have to memorize them. UN, let's see, C9H10O2, ignore the oxygen, becomes C9H10. So it's 18 plus 2 is 20. 20 minus 10 over 2 is 10 over 2 equals 5. Okay, same, kind of like the last problem. You also see the benzene. You immediately say, it's a benzene. I don't like to take shortcuts, though. I always make the table. Okay, so delta split H. The reason I make the table is because that leads to the substructures. And with the substructures, you can start snapping them together, right? Okay, so now it's like 1.5 triplet 3H, 4.2 quartet, Q, quartet, 2H, 7 to 8, I just say 7 to 8 is molt, 5H. Okay, cool. So go down the table now. I'm mostly looking at integration, and I say 3H and 2H. I see CH3, CH2, CH3, CH2, right? And then that, we just like before, you know, it's a benzene. It's in the 7 to 8 region. It's a benzene. And is this monosubstituted or disubstituted? Mono or di? I see mono, and yep, you're mono. It's totally mono, right? Because 5 hydrogens means 1 connection, right? 6 positions, 6 minus 5 is 1. So it's monosubstituted. We'll do disubstitute in a bit. Okay, are we done with that step of identifying the substructures? Well, no, we're not, because we count everything up and we're missing the oxygens, for example, right? It looks like that's 1, 2 plus 6 is 8. 8 carbons. Okay, we're missing a carbon. Hydrogens we should have. 5 plus 5 is 10. So we're missing a carbon and we're missing 2 oxygens. Okay, now we have a non-ketone mystery functional group. The last 2 problems is ketone. What do we do now? We have a carbon and 2 oxygens. A carbon and 2 oxygens. Go into your little toolkit of functional groups and you say,
Carboxylic acid.
so somebody said carboxylic acid, and that's a great guess, and it is wrong. And but it's good you're thinking carbon, 2 oxygens, carboxylic acid, right? The reason you know it's not a carboxylic acid is because it would have an extra proton, right? A carboxylic acid is not just a carbon and 2 oxygens, it's a carbon and 2 oxygens and a proton. And that proton, if you look in your chart, is way at 12, right? You don't see it, so it's not this. But I see in the comments the correct answer, which is ester, right? Because this minus the proton's an ester, right? Cool. Wonderful. All right, so it's an ester. It's the reason it's not an acid is because that would have an extra proton. And the other thing is we already counted for all the protons, right? There's 10, right? 5 plus 5 is 10. Can't be a carboxylic acid. Somebody said, could it be an alcohol? Somebody in the comments said alcohol. It can't be an alcohol either, because also an alcohol would be an extra proton. We don't have any protons to give up, so absolutely, positively an ester, okay? So what's our, now we're at a milestone. We have the pieces. Now, I'll kind of ask you guys, how should I proceed? I need to start attaching stuff. Sometimes I'm, you know, I love the splitting, right? I love the splitting because that tells you connectivity, right? Remember when we learned about splitting, we said if you ever have a quartet and a triplet, it's probably a quartet and a triplet. Well, what does a quartet mean about the CH2? Quartet means how many neighbors? Quartet.
3.
N plus 1 backwards, right? Quartet is 4 peaks, means 3 neighbors. Oh, wow, the CH2 might be connected to the CH3. Ah, right? Because quartet would be 3 neighbors. And I'm looking at that methyl and I'm like, it's a triplet. How many neighbors would this CH3 have? It must have 2 neighbors. Oh, wow. Okay, now I know the CH3 and the CH2 are connected, right? It's an ethyl group. Okay, get the eraser out. All right, this is slightly more complicated than the last problems because now we have an additional step. Yes, we have 2 end pieces in the middle piece, 2 end pieces in the middle piece, but the funny thing about this middle piece is it can go one way or the other, right? It can go oxygen connects to the CH2 or oxygen connects to the benzene, right? Right? This could go one direction or the other direction, and it'll give you different answers, and one's right and one's wrong, right? So the answer is what? What piece of information will give us away? we've already used splitting up. There's nothing, no more information in splitting, but we look around and we're like, I see the shift. Yeah, shift of what? Maybe the shift of the CH2, right? 4.2. Remember what? Maybe I can't easily show my table of chemical shifts the way I'm doing this. Maybe I can. I don't know. Give me a second. It's on the syllabus. One second. I'm gonna make a printout real quick. One second. Okay, so I was saying, you know, the 4.2 really means something, right? And that means something about the CH2 might be connected to something electronegative, like, well, it can't be to the benzene, right? It's probably the CH2 is connected to the oxygen, right? So if I look at my chart, remember this? CH or CH2 or whatever, where the carbon is connected to an electronegative atom, 3 to 4 region, right? And furthermore, while we're looking at this, what is the 2 to 3 region? Usually, it's a CH on a carbon next to pi bonds, right? Because we're going to see that in a second also. Okay, so keep those in mind, right? All right. So, yeah, absolutely, the oxygen is connected to CH2. That's the take home here. And if the oxygen is connected to CH2, then the C double bond O is connected to the benzene. So this is just this ester. That's the answer, right? We all got it? Because what's the other option? Let's just do the other option. Let's draw the other option, which should be wrong. When I said earlier, like generate candidate structures, this is a candidate structure. This is a candidate structure. Oh, okay. So, and somebody else, I got some cool comments we'll discuss in a second, all right? But let's just look at this one real quick. All I did is I switched the ester around, right? If I had this, where would the CH2 be? Remember my chart? Let's get the chart out again. Because where are signals if like a CH2 was that next to a pi bond? It would be in the 2 to 3 region, right? So this, if you had this, it would look very similar. It would look identical to this, except the quartet would be over here, right? The CH2 quartet would be in the 2 to 3 region. So this would be like 2.5 or so. That's my prediction of this. So that's how we know it's this and not that, okay? Can I zoom out a bit? I can't. The way I have a webcam set up, I can't really zoom out. Sorry, guys. Hopefully you can see it a little bit. Okay, there's nothing else to see. Okay. Okay. All right. And one more question. Somebody said, could it have been benzene CH2 ester CH3? That's a great question. Benzene CH2 ester CH3. Let's draw that. Benzene CH2, and then like, I don't know, say ester CH3, something like that. That would be benzene CH2 ester CH3, right? Why can it not be this? What would be wrong with this? This would have a problem that's inconsistent with the data. And that is the neighbors, right? The splitting, right? This would be a singlet and that would be a singlet. Be singlet and singlet, right? If these were singlets, yeah, maybe. But, right? So yeah, kind of cool, huh? That's why I love to use that splitting really early on to use up the splitting information to figure out what your multiplets are, right? We cool? All right, let's keep going. Okay, a non-benzene. Scary, scary, non-benzene, right? This is not a benzene. And UN is C4H10. Even scarier is I don't think there's even any UNs. I think it's UN equals 0, right? Okay, so no ketones, but we might have a mystery functional group still. We'll see. Actually, no, I think if UN equals 0, you're not going to have a mystery, but let's make the table and go from there. Okay, so delta split H. Delta split H. All right, I'm going to go left to right this time. 3.5. Doublet. H's are 2. 2.0. Ooh, signal that disappears with D2O addition. Uh-oh. But let's for now, I am gonna write singlet and 1, and I'm just gonna say disup D2O. Of course, that means something, but we'll get back to it. We have a multiplet at 1.7, which is a single hydrogen. And then at 1.0, a doublet of 6. Is that the table? You think that's the table? Right? Next, we will make the substructures. So for the most part, I'm just looking at integration right now, right? Like 6 is very obviously 2 methyls. 1 multiplet is probably a CH. It's a CH with 3 squigglies, right? Now this guy is a little weird. Singlet, it disappears with D2O. I happen to have an oxygen in the molecule. So what do I say? Probably an alcohol, yeah. Somebody said alcohol. And how do I draw a substructure for an alcohol? And how many squigglies are on that substructure? Well, it's just this. That 1 squiggly, right? An alcohol has 1 squiggly, right? What do you think this is? 2. What's your best guess? I see CH2. I see CH, I see CH2. It's definitely CH2, yeah. Okay. Now we will go through all these and see if they add up, right? 1, 2, 3, 4 carbons. Oh, good. We have 4 carbons. Hydrogens. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, good. Oxygen. Okay, we have an oxygen. All right, good. This is a good place to be. Now we're going to start snapping things together, right? First you make your pieces, then you start snapping them. The doublet at 1.1 ppm, doublet, 6 hydrogens, you got CH. That immediately jumps out at me. Another point is there's multiple ways we can do this. I might say, oh, 3.5, the CH2 must be connected to what? 3.5, it's kind of downfield, that's CH2. Maybe it's connected to an electronegative atom, like, I don't know, what electronegative atom do we see? 3.5,
Yeah.
ooh, of oxygen, right? So I could say, well, that's connected to that, right? Like, so it's up to you kind of where you want to begin. Sometimes you'll begin and go down the wrong path and you get stuck and then you have to start over. But I think we can make 2 deductions. These guys are connected and these guys are connected, right? So I love that doublet. The doublet is, you know, unmistakable. The doublet, actually, that's unmistakable too. Doublet absolutely means these are connected to a CH. There's only one CH. These guys are connected. So erase everything and draw an isopropyl group. Maybe I'll. There's actually two ways you can proceed at this point. You could just see the answer because we have a middle piece and two end pieces, right? Middle piece, two end pieces, and just see what the answer is, right? Middle piece, two end pieces. Or I can just say, well, these guys are connected, and then I just have two pieces. But the bottom line is we're done, right? It's that. You could draw it however you want. I could draw it in the kind of each carbon and hydrogen, or get into this kind of zigzag mode, and we see what the answer is. Isopropyl group, CH2OH, right? Cool. Next. Scary problem number 5. Looks intimidating, but it's not that intimidating. UN, remember we dropped the oxygens, it's C5H10. Okay, and it's 1, yeah, UN equals 1. Okay, so maybe some kind of mystery functional group. Let's do my delta split H. There's going to be my table. Delta split H. Maybe I'll start with 1.0 and say it is looks like a triplet. Do I say that? It's a triplet, yeah. And it's 3H. Okay, now this looks crazy. 1.7-ish. We have a multiplet, which is just like a bunch of craziness. How many H? It's 4H. Oh, that looks scary because you can't have a CH4, right? A methane, right? You can't have a CH4. That doesn't make sense. Maybe it's 2 CH2s though. That's a possibility. We also have a CH2 at 2.1, which is a triplet. Cool. All right. Now this crazy guy over at 12 ppm disappears with D2O. So somebody said alcohol, but that's not exactly right because let's think a little bit further about this, all right? You may go look at your chart. 12 is pretty far down. We also have a UN equals 1, so some kind of mystery functional group. We also got a couple oxygens, UN equals 1, 12. Maybe let's get the chart out. Yeah, somebody said it. Yeah. Acid, 12, right? Yeah. So that 12.0 or whatever is a singlet. It does disappear D2O, it's 1H. It's probably a carboxylic acid, but let's it can't be an ester, right? Because an ester would not have that. Let's just do our substructures now, CH3. Now the 4 might be weird to you because we haven't seen that yet, but sometimes peaks just come at the same place. And so it's probably a pair of CH2s, just 2 CH2s. So and then that's just another CH2. And what about this guy? we decided it's a carboxylic acid. Well, how do I draw a carboxylic acid as a substructure? Well, I just started the squiggly and write C double bond O, OH. Okay. Now with basically no thought at all, we know what the answer is. Because you have 2 end pieces and 3 identical middle pieces. It's a long carboxylic acid. It's how many carbons total? 1, 2, 3, 4. It's a 5-carbon carboxylic acid, right? It's a pentanoic acid. One, 2, 3, 4, 5. Which, of course, there's the CH3, which is the triplet. Why is it a triplet? Because we didn't even look at the splitting, really, right? But once you got the pieces, the answer was obvious. Because if you have 2 end pieces and 3 identical middle pieces, there's no more thinking, right? But of course, the CH3 is a triplet because it has 2 neighbors, right? What about the carboxylic acid's weird? Well, it's not that weird. Why is it a singlet? Because there are no neighbors. This cannot see like the neighbors on the other side, right? The neighbors are too far away. Okay. Yeah, cool. So that is the yeah, that's why that's a singlet, right? What about this? This is the downfield CH2 of the chain. 2.1 is a triplet. Which one is that? Where is it? It's a CH2 that's a 2, which is this one, right? Why is it at 2.1? Because it's what comes between 2 and 3? Next to something kinds of bond, right? Next to what? It's next to pi bonds. And of course, that's a pi bond, right? So this being 2.1 is a triplet because there's 1 neighbor of a CH2, but it's a triplet because there's a CH2 next door. It's at 2.1 because it's next to a pi bond. Remember that? 2 to 3, CH next to pi bonds, right? Okay, cool. So that was not that hard of a problem. It's just another example. Is it the same if the structure is reversed? Somebody asked me, is it the same if the structure is reversed? And that's absolutely the case, yes. So if I did this, it's the same molecule. You could draw this 1,000 different orientations. It doesn't matter how you draw it. That's the same. 1, 2, 3, 4, 5. Yeah. As long as you don't lose a carbon, you're all good. Okay. Fun. Are we having fun yet? Some people are either having fun or kind of concerned, but I think it's pretty fun. This is so easy. This problem is so easy that I'm gonna expedite this one a little bit. C9H12, UN equals, I think, 4, I think. 1820 minus 12, 18, 8 minus 8 divided by 2 is 4, yeah. This is too easy. This is too easy. Of course, the 5 is a benzene. Monosubstituted. We've seen this pattern 1,000 times now, and it's an isopropyl group. Isopropyl group. The answer is isopropyl benzene. So we could have done the whole chart table method and got the same answer, but this is so easy. Easy peasy. Okay, 7. Now this, in contrast, is a little crazier because this is the same molecular formula, C9H12, UN equals 4. And this is a case where my method kind of fails us a little bit, but let's do it anyway. Okay, so I am going to, UN equals 4 immediately says what? UN equals 4, probably a benzene, right? It's a benzene. But I see 1, 1? That's weird, right? So let's do it. We'll get stuck and then we'll figure out the answer. Delta splitting H. So 6.8, singlet 1, weird. 2.1, singlet 3, okay, we're cool. And yeah, somebody said, oh, the ratios, and you're exactly right. This is that ratio issue. Remember the ratio issue we had? Okay, because now we're totally lost. 1 and 3, how does that add up to 12? And the answer is, you got to kind of, this is a case where you have symmetry or something, and 1 to 3 is misleading. So maybe if you multiply this times 3 and that times 3, this becomes 3, this becomes 9. Okay, now it's going to be a little more doable. All right. So I'm gonna go through this one kind of quickly because I want to do another problem or two. But basically, okay, we got a benzene, right? It's a benzene. We're absolutely in the benzene region. It's got 3 H's on it. So is this a monosubstituted, disubstituted, or trisubstituted benzene? There's 3 H's. So on the benzene, there must be 3 things. So you have like a couple options of this. I'm going to draw the wrong one, and then I'm going to draw the right one. I'll explain why the right one is right in a second. The right, this is the correct one. Oh yeah, and then also what's 9? 9 at around 2. What is that? 9 has to be what? 3 methyls. 3 methyls. That's easy, right? CH3, CH3, CH3. Okay. So let me just, I'm gonna expedite this problem because it's a little kind of beyond what you're gonna see on the quizzes anyway. But yeah, it's basically this with 3 methyls on it, right? It's trimethylbenzene. See how that would be consistent with this data, right? And I see, is less strain on the right? Somebody asked, is there less strain on the right? Well, that's actually not the way to think about it. It's like, okay, why is it this and not this? Why is it equally distributed versus like 3 things that are bunched up? And the answer is something, and somebody said stability or stable. It has nothing to do with stability. And remember, we can draw NMR of unstable molecules, right? The issue is, if it was this, if it was the one on the left, then these guys would be the same, but that would be different, right? These would be the same, and that would be different. And the fact that you have this very overly simple singlet, this is a singlet. That means that would be consistent with like 3 identical CHs, right? 3 identical CHs, right? And that would be the case if you had the squigglies like equally distributed, because these would be identical, 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 right? So somebody said on the left, would we get different splitting? And the answer is yes. This would be weird because these 2 are the same and that's different. So it wouldn't be as simple as this, right? The other one you could imagine is this, right? I got 3 squigglies. What about this? Well, I got 3 squigglies and 3 H's, right? H, H, H. Well, these, in this case, all 3 CHs could be different, right? So this would also not, but both of these are impossible for this, or very unlikely. These trisubstituted benzenes would be unlikely if you have a simple singlet, right? This would be way more consistent with something like this, where everything's identical. H, H, H are identical, right? Okay, so this is a little weird. I want to keep going because there's a couple more fun problems. Okay. And we have maybe time for one more problem. Let's do this one. We have 3 minutes. We'll do this quickly. All right. UN is what? It's 9, 18, 20 minus 12. I think it's 4. If I'm wrong, tell me. Table. Okay, I'm gonna go left to right. 7.2. Splitting is a singlet, 5H. 4.5. Triplet, 1H. Right? Another OH, probably 2.1. Is a singlet. This is actually a little bit of a broad singlet. Sometimes those OHs are a little broadened out. So I say BS for broad singlet. 1. Quintet. 1.9. Quintet. 2H. Triplet at 1.0. Triplet. Okay. Is my table right? I think my table's right. Okay, so I'm going to quickly 5H benzene, right? Monosubstituted. Uh, 1H is a CH. With 3 squigglies. Broad singlet. What do you say? And we got an oxygen. Maybe it's a OH. Quintet. We got CH2 and a CH3, right? CH2, CH3. All right, we cool? Starts, I think we can assume everything's accounted for. 6, 7, 8, 9 carbons. H is 5, 6, 7, 8, 9, 10, 11, 12. Yep, everything's accounted for. Okay, let's see, to save time. The 4.5, the CH is probably next to the oxygen, right? So I'm gonna draw that over here. Okay. And then also maybe the triplet, CH3 triplet must be next to the what? CH3 triplet must be next to the CH2, which is ethyl group, right? Two end pieces, one middle piece, done. Isn't this cool? It's a really universal strategy. I'll draw the problem, then I'll stop the recording. That's the answer. All right. Okay, so I'm still deciding on whether we're going to have the quiz on Tuesday. There is a possibility I'm going to just postpone because we're not really in a rush. I kind of want to do a couple more hard problems and then maybe do the quiz the next week. But I'm going to make that decision maybe tonight and over tomorrow. I'll let you know by tomorrow though about the quiz. Remember quiz 1. Oh yeah. I want to say yeah. Quiz 1 is the silly one that's up right now. Quiz 2 would be like a slightly, maybe one challenging problem, kind of like this, right? But I think we might need a little more work. You guys are doing pretty good, but we might need a little more work. Okay, so I'm going to stop the recording and I'll hang out for a bit. Yeah, we have some more examples. I wouldn't do all of them. If you want to, how about this? If you want to practice over the weekend, try a couple of the other problems, right? And yeah, and whenever we have quizzes, I'm going to give you a hint, usually on Friday, and what it's about. Hopefully you guys enjoyed this. Have a wonderful weekend.
Thank you.
Thank you.
Thank you.
Thank you.